Hi, my name is Jay Lewis, and I'm a engineer for the renewable energy spacecraft, vertical farming, uh, mostly systems and reliability. My favorite thing are simulations, and today uh, I will walk through some of the preparation for basically avoiding simulating things you don't need to simulate. We can build on work by others. Uh, this article brings up a new consideration that you've probably heard of Kessler syndrome, that is a concern. Um, Spacecraft in the ocean, spacecraft crashing into people on land. There's all these concerns. This is a new one. Um, so they're made out of aluminum, for the most part, aluminum alloys, and when they burn up in the atmosphere, it vaporizes. So what does having all this aluminum vapor do to the atmosphere? And it's very high up, so it stays there, for a long time. Um, Essentially, we don't know. So this article brings up the issue and doesn't resolve it. Um, it so it's part of the motivation for um, why we don't uh, want to leave everything. Um, I think we should salvage it. The fact everything is made out of aluminum and aluminum's the most salvaged metal on Earth. Huge recovery rate. Yeah, we should try to salvage it if we can. So, where is all this debris? Um, this is a typical article uh, talking about the problem. A nice artist rendering. Uh, it's very funny in a way that this is Florida. Um, Somehow we're this far from the Earth, but this satellite is not much smaller than this one, even though it's almost halfway around the Earth. So, if we use the closest one for a reference, the rest of these should be either like this one might be a dot. It's so far away, and the rest are you couldn't even see them from here. Just as if you were standing in Florida, you're not going to be able to see uh, a plane, so far over the horizon. I mean, even without the horizon, we just can't see things that small. It's not realistic. This is a lot more realistic. The scale's still wrong. These satellites are not nearly that large, but they used a real database. I believe this is up to date from 2019, since it's um, in the file name. Uh, they're talking about 1 millimeter. So this is tracking uh, very small particles, including up to entire rocket bodies and spacecraft. Includes the debris and meteorites. There's stuff that's been in orbit for millions of years. It's still there. Um, so uh, I've found a NASA summary of what is the distribution of all of this. So this is a chart from I pulled out of this article, and it's out of date, but the gist of it should be right, and that's good enough for now. Um, the bottom is interesting. At 500 kilometers is the bottom end of this chart, and it turns out that's actually pretty interesting. Um, I'll cover that next. 500 are 1 meter in diameter, so this is a meter's about a yard. So this is decent sized objects. RB means rocket body, and a SC is a spacecraft payload, a satellite. Um, so most are in this range. So 500 to 1,000 is the vast majority. There's a few above that, but very sparse. And an interesting to think about is the thing of these is concentric rings. So every time the circle gets bigger, the there's more space in between things. So at 500, um, that is a circle much smaller than at 1500. And so not only is this sparsely populated, it's also in a much larger, an orbit with a lot more area to cover. So, if you're doing a aluminum salvage operation, um, there's no point in going there. That's just so far out. But look at this. This is a really good place. Why is 500 so important? Um, and and one possibility is because atmospheric drag causes deorbiting, and if you don't do anything. So I found some MATLAB code, very generous. Oh, that's interesting. Just realized this is a different code than the one I just found. I found another one. I think it's the same one though. Yep, Darren Koblik. Okay, this is actually the same one, just different. He has a README file that has different text. The uh, there's a This is a lot of detail, and he is taking into account a lot of factors like the sun and a thing like a lightweight thing with a large surface area will catch more wind essentially than like a solid sphere. So this is a very good model that considers a lot of detail, and I really don't care about that. So I ran the code um, for a generic piece of debris uh, to see how long does it take to deorbit. And the 200 kilometers the same day. So anything at that height will catch more and more wind and just deorbit. The 350 will take 6 months, and then ISS is just above 400. So essentially, if they throw something out the window, out an airlock, 6 years later, I'm sorry, 2 years later, it will be pulled down into the atmosphere. Um, Anything at 450 will take 6 years, so roughly triple the time. Another 50 kilometers higher will take about triple the time. And then another 50, almost triple again, a little more than triple. So if we go back to this, so we saw at 550 would take 66 years. There's almost nothing in that range. Um, and if we're tripling every 50 kilometers higher than at 600, that should take about 150 years, and then another tripling, 450 years. So as you're going further out, essentially it's just indefinite. These objects are here to stay, which from a salvage point of view is good. If you're looking to save an object at 450 kilometers up, and 6 years from now it will be burning up in the atmosphere anyway, by the time you get to it, it will already be on its way down. So everything in this range is not a really good candidate, even if it's crowded, even if there's a Kessler syndrome. Um, from a salvage point of view, probably not worth it. This medium range maybe. Um, so I guess I'll take back what I just said. Because if you had, let's say, had a scrap robot in in this orbit already, then maybe this is the best place to put it because you're saving it from uh, burning up in the atmosphere, whereas everything at a higher orbit, it's not going anywhere. So the overlap really, it's really hard to say. I think that for now, we should consider. I'm putting uh, I'm considering the ISS. It's right in between. So everything above the ISS, we'll say, is worth considering on a salvage mission. And that so the advantage to simplify the model, this higher orbit, you can just not worry about drag at all. You don't have to use any of this code. But once you're closer to the ISS, this 2 to 6 year period starts to get 6 years is yeah. So I've got this data handy. Um, so the next step is I have an intuition that why is this? I have an intuition that on this chart, what I'm showing is the two derelict iridium. There's several derelict iridiums in orbit. I'm showing two of them, the lowest and the highest. They're at the 600 and 1000. This is, part of that debris field we in the other slide. So if 200 gets it safely below the ISS and quickly will burn up, which is the default plan, if you look at everybody that is planning to do this, um, what if you go up for this low one, you're going up 500 kilometers uh, into this 1,000 range, which there's not much there. Um, so the thinking is if we're having a place like a salvage yard to take these two to be turned into raw aluminum to use for other things in space, then one place to consider putting it would be around this 1100, um, and the higher ones are almost there now. So the next step is to understand more what is going on, and also my intuition is how much energy does it take. Um, so this is a good summary. Um, I'm not going to go into the math here. The orbit transfers. So let's say you want to take a chunk of debris from its current orbit to a safe uh, recycling place in a different orbit, a higher orbit. Um, it will take energy to move it there. If you want to deorbit it, it will take energy to move it down. My intuition is that these are roughly equal, and maybe it's a little bit more, a little bit less to go higher. Maybe it depends on how much higher. Uh, so that's one problem to solve. And then the other problem is where do we get the data? And I found a few places. So I'm not going to go into that right now. That's for another time. Uh, let's see. So let me wrap up. Um, Thank you for watching. I appreciate your attention, and it would be great if you could hit the subscribe button and the like button. Do not hit the bell. I don't know. I do know why people say that because they want more views and the algorithm likes it, but the algorithm should work for us. Don't turn off your YouTube notifications. You probably have better things to do. I know I do. Goodbye.